Recording is on.
Awesome. Thank you so much. Okay, very well. So welcome everyone. It's my honor to welcome all of you here. We got 40 people at this call, so great attendance. Many people excited to see Ben. So yeah, a huge honor to welcome Ben Edgington here for our first session in the second phase of the study group. Uh, so Ben accepted our invitation to give a lecture as a part of the protocol study group. And he's going to be diving into fork choice and the mechanisms in the consensus layer. And I believe that he's like probably the best person to talk about this. You may know him as a former Teku developer, so he's been actually working directly on the consensus client. Later, he was working with Optimism layer 2 on Ethereum, also closely following the protocol. But he's probably the most famous for his E2 book. Um, and by the way, huge respect, Ben, for always sticking with the E2 and never accepting the new nomenclature. Like that's great. But the E2 book is of course about consensus, and it's annotated specification of the consensus layer. So probably the best way to learn the details about the consensus and uh, all the difficulties with proper context and explanation. So yeah, thank you so much for being here, Ben. It's an honor. With your talk, we are starting this new phase with the study group before people watch the existing recordings and existing materials, but now we are creating new ones. We will be covering every part of consensus layer, every part of the execution layer with 2 sessions a week. So we are starting now Monday with the fork choice and the consensus. Yeah, that's it for the intro. I think the stage is yours now. So yeah, go ahead.
Thank you so much, Mario. I appreciate the warm introduction. It's a pleasure to meet with everybody here. The proto core devs is wonderful. This is probably the best looking slide in the presentation, not just because it's got my face on it, but the rest of it is just a dog's breakfast. So don't criticize me for that, please. Just brief intro. I discovered Ethereum somewhere in early 2016, and that marked the transition from what I refer to as my suit and tie wearing years to my hoodie wearing years when I joined Consensus in late 2017. I did a bunch of stuff there, including, as Mario says, overseeing the Teku team. I didn't write a lot of the code, but I found fabulous people who have turned it into one of the leading consensus clients now. I left about a year ago, just over a year ago, joined OP, little sojourn in L2 at Optimism, and I recently left again, and I'll tell you why. The green stuff down here is the kind of hobby weekend evening work that I've been doing over the years. For 4 years, I published What's New in ETH2, a sort of bi-weekly newsletter on the consensus protocol as it developed. But the main thing Mario's already referred to is this upgrading Ethereum book. That's the official title, not the ETH2 book, but you can find it at eth2book.info. And it's a bit stale. I'm nearly 2 hard forks behind. It's about a year and a half out of date. I haven't done any work on it whilst at Optimism. So the idea is now to pick up that work and spend at least the next year just bringing it up to date with Deneb, Electra, Fulu maybe, and fleshing out the content in there so it's complete. I will be linking a lot in this presentation to the material in there. There's just too much to cover in one presentation like this. So if you want to go deeper, it's all there. Right, let's get on with it. Easy agenda. Quick intro to fork choice stuff. We're going to look at LMD Ghost. We're going to look at Casper FFG. We're going to look at how they're combined into Gasper. And then I'm really hoping to leave some good time at the end for some AMA, either about fork choice or anything else about core dev life. Yep, so let's get into introduction to fork choice. So I think you've had Alex Stokes, or there's been a presentation, maybe you've watched by Alex on basic consensus stuff. I haven't really got time to recap all of that, so I'm going to skip through this, but you've got the presentation, you can follow the links, and they'll take you to the relevant parts in the book. But useful concepts to know for this session: safety. So colloquially, nothing bad ever happens. So we have a distributed system. There are nodes all over the world. They're all communicating via this unreliable network. Some of them may be adversarial, some of them may be faulty, or resource constrained or slow or whatever. But this network is trying to come to agreement, and if it's a safe network, then nothing bad ever happens, which means a reorg maybe, or a double spend, or inability to progress the chain, or inability to finalize the chain, I should say, something like that. Counterpart to safety is liveness, which is also known as availability, and this is the idea that something good eventually happens. So the idea is that we can always add blocks to the end of the chain, for example, or we can always continue to finalize the chain. Something good eventually happens. And there's a theorem called the CAP theorem, consistency, availability, partition tolerance theorem, which basically says you can only have two of these three, and partition tolerance isn't really reasonable on a real network like the internet. There are always going to be partitions where some part of the network can't talk to another part of the network. So in those circumstances, we have to choose whether we're going to favor consistency, so our system is always in a well-defined state and every node agrees with every other node, or we're going to choose availability, which means that our system can continue working even in the presence of partitions, like as happens on the internet. It's a very simple theorem and quite easy to understand where that comes from. And the point is that Ethereum prioritizes liveness. So we have this LMD Ghost protocol, and the idea is that even if there's a big partition of the network or half the nodes go down or something like that, what remains, what you can see locally, will still continue to make progress and add blocks to the chain. And that's a design decision. Not all chains do that. So Cosmos chains, for example, prioritize safety. But on top of that, we add this kind of best efforts finality gadget. So we'll come to that in much greater detail. So we kind of guarantee liveness, and we have best efforts safety, and in combination we call that Gasper. So that sets the scene. We'll be unpacking all of that as we progress. Now, the challenge that we have before us is that networks that prioritize liveness tend to be forkful. If they weren't, they would be safe because everybody would agree with each other all the time. But because nodes disagree, because of late messages, or because an attacker is feeding different messages to different nodes, or because of faulty software or something like that, they have different views of the network at any given time. And this results in what we call forks. So we end up with a block tree rather than a block chain. And here we have a block tree depicted. We have a root, which it's lying on its side, this poor tree. It has its root at block A, and then it has branches which come off that. So a branch that ends in block C, branch that ends in block F, branch that ends in block E. And where there are multiple branches coming out of a block, so it has multiple descendants, we call that a fork. And our task here is to choose between forks. So that's the purpose of the fork choice rule. It's a method by which the network converges on a single branch and therefore a single shared history. So what we're doing is turning this block tree into a block chain, which has just got a linear history going back, and we prune out the blocks which are not canonical, not included in that branch. And how do we do this? Well, there's a kind of heuristic. I mean, the goal is based on the information that we have about the network, which we receive through blocks, which we receive through peer-to-peer information, which perhaps we receive via carrier pigeons, whatever it is. Based on all the information we can gather about the network, we try to build a block on the head of the chain that is least likely to be orphaned by other nodes. So we build a block on the head of the chain that we believe other nodes in the network also think is the head of the chain. And if we all agree, then we've converged. We have a unified view of the network. So we have to somehow guess based on this potentially faulty, potentially late, potentially incomplete information we have about the network. We have to guess which block most of the network thinks is the best, is the one that they would build on if they were in our shoes. And then we have convergence onto a single view. Right. So far, so simple. I mean, that's the sort of basics of fork choice, and we just make this choice. Here be dragons. This slide is a partial list of issues with Ethereum's proof of stake fork choice going back in time. It's not going to go into all detail now, though we will revisit one or two of these in slides to come. And although it can look superficially quite simple and the concepts are not too hard, it turns out to be fiendishly hard to reason about. There are horrendous edge cases, and it's very easy to get stuff wrong. And this kind of ignominious history is testament to that. So there are links to all sorts of exciting attacks on the chain that people have discovered. Now, we think we've fixed all of these right now. But yeah, nonetheless, I wouldn't bet on there not being more issues in there. And the other exciting thing about fork choice is it's not operating in a nice, clean, isolated environment. It has to operate in conjunction with the real world. So 2 weeks ago, the Holsky testnet was upgraded with Pectra, and it was, shall we say, disaster. And I've linked here to the start of the conversation on Discord from that evening 2 weeks ago. And if you can follow along, so 40 hours in the life of fork choice, if you can follow along that conversation that the current devs are having or had about how to get the network to converge onto one chain after it fragmented in Holsky, then you're 90% of the way to being a core dev. I mean, it's goes into everything. And the fork choice was fighting against, faulty clients were the cause of the initial incident. They disagreed on the block validity. This led to kind of peer-to-peer meltdown where nodes couldn't find each other, couldn't find other nodes on the same chain as them. So blocks weren't getting propagated, attestations weren't getting propagated very well. And then there was all sorts of interference from slashing protection kicking in, low levels of block production. Clients were offline trying to get back online. They were hampered because there weren't snack sync servers. Checkpoint sync was difficult because it relies on finalized checkpoints. Optimistic sync also caused problems because of the window of availability of it. Clients were going out of memory and falling over. It was extraordinary. And amidst all of this nice platonic fork choice rule that we have has to kind of handle all of this and come to agreement about the state of the network. And rescuing Holsky has been educational. So moving on from the kind of challenges, we get kind of into the specs here. I will show some code in the course of the presentation. We've got this object, this attestation data object, and this is how nodes communicate with each other. They communicate with each other in two ways. One's through attestations, and there are hundreds of thousands of these every slot, and also through blocks, of which there is one per slot, ideally. And so the main way nodes communicate with each other is via attestations. And so each validator on the network broadcasts its view of the network via an attestation. It does this once per epoch. So every validator that's got a stake has the opportunity once per epoch to broadcast its view of the network. And primarily via peer-to-peer gossip, but attestation is also packed into blocks by block proposers. So the record is there. What are the contents of an attestation? Well, you have a slot number just so you can anchor it in time. The committee index is historical. After the Electra upgrade, this will be set to 0 all the time, so don't need to worry about that. And then there are two kinds of vote, and this is what we're going to focus on now. So this is the what feeds fork choice. This is the raw material for running fork choice. Two kinds of vote: LMD ghost vote and FFG, which is Casper FFG vote. And LMD ghost votes are for a block, so you vote for the root hash of a particular block, and FFG votes are for 2 checkpoints, and we'll look into those more later. And the two consensus mechanisms that we have, LMD ghost and Casper FFG, operate on different timescales and via different mechanisms mostly. So LMD ghost largely depends on attestations received via Gossip. It's a kind of real-time protocol. It has to make quick decisions on the order of seconds and doesn't have time to wait for attestations to get into blocks. So in the specs, this occupies its own document, which is called forkchoice.md, and Casper FFG depends only on attestations that are being packed into blocks. So handling of those is part of block and epoch processing. So you'll find all the stuff about that in beaconchain.md document. We're going to focus on forkchoice.md in this session. But yeah, that's just to help you kind of orient yourself in the specs. And the other thing that matters is the store. So this is the node's view of the network, what's classically called a view in classical consensus theory. This is all the information that, and absolutely everything that a node needs to know about the state of the network outside. This is all the best information it has about the state of the entire network, and it's called the store. It had started life very simple. So these lines without a red asterisk were the original ones in the early versions of the spec. Over time, the lines with asterisks and these objects and structures have been added solely to fix issues that have been found over the years. So that's just another sort of hint that everything is more complex than you would hope it would be. It has grown into a bit of a monster there. So that's the store. And the third interesting thing about kind of fork choice is LMD ghost fork choice is it's event driven. So there are handlers which you can find in that forkchoice.md document. And there are 4 handlers effectively on tick. So the fork choice store, the store is regularly updated. It updates its current time, which is at the top of this store object here. Every time a tick happens, I'll tell you what a tick is in a moment, and it does some light housekeeping as well. It's a very lightweight function. A tick is just a regular call. I mean, it could happen like twice per slot. In Teku, we did it twice every second, so every half second. We'd perform a tick, and the fork choice would update its time and do some housekeeping. More interesting is on block. So this is what happens when my node receives a block on the wire from anywhere. Then this event is triggered on block, and the handler adds blocks to the store as and when the node receives them. On attestation, similarly, anytime an attestation is received via any means, whether it's in a block or on the wire, then it updates the validator's latest messages in the store. So we have this latest messages field at the bottom, and on attestation updates that field. And then we have this on attester slashing, which was added later just to avoid an edge case where validators could be slashed but still count within fork choice. And so we need to know if they've been slashed and discount their votes. It avoids some attacks where validators can vote. They can equivocate, they can contradict themselves and make multiple votes. And there's some latency in the slashing, so that deals with that. And so because it's event driven, the fork choice is always ready to output a best head block anytime I want to call it. If I need to make an attestation or I need to build a block and I need to know what to attest to or where to build, I just call the get head function on fork choice and it will spit out a block and say, there you go, attest to this, build on this, and I'm done. Right. That's it, whistle stop intro stuff. Let me just pause as promised for any questions. We will be looking at LMD Ghost next, and then Casper FFG. Anyone want me to clarify anything there?
Hello. I wanted to ask about the job and the work that proposers do in collecting the attestations and packing them into blocks. So are there any incentives, either rewards or punishments for doing that or not doing it? And like, what if I'm a proposer who wants to save a little time and not do that? Can you help me through that a little?
Yeah, there are no direct incentives to pack attestations into blocks. However, there is a minor incentive to do so, which is, I cover it in the book a little, is that my reward as an attester is proportional to the number of attestations they get on chain. So if 100% of attestations get on chain, I get a full reward. If only half attestations get on chain, I only get half an attestation reward, and so does everybody else. So if I want to make sure I maximize my attestation reward, then I need to make sure that as many attestations as possible get on chain, which is my sort of indirect incentive to pack attestations into blocks. Does that make sense?
Yeah, definitely. Thank you.
Yeah, a quick one for the attestation, the beacon block route. Are you voting on what is the previous block that everyone else is voting on for this round in the slot? Or is that you saying, like, this is what I think now will be the current head of the block, like the new hash?
Yeah. So Alex's presentation covered this a little bit, but so a block is supposed to be broadcast within the first 4 seconds of a slot, and we'll look at that a little. And then at the 4-second mark in a slot, I'm supposed to attest to that block, whether I've seen a block, in which case I attest to it, or if I haven't seen a block, I attest to the previous block. So I declare it's an empty slot. So that's the timing and what I attest to. So at 0 seconds, the block's supposed to be published. 4 seconds for it to propagate. At 4 seconds, I make an attestation and broadcast it. And at 8 seconds, the aggregators start aggregating attestations ready for the next block proposer at 0 seconds, 12 seconds to propose the next block. Does that answer your question?
Yeah, it'll be this block. Yeah, that's at 4 seconds. You send out the attestation data, and it'll be the what you're saying is now the new beacon block route.
Yep.
Sorry, I've been talking on mute. Okay, so what is the optimal way for validators to send the latest messages, whether it's blocks or in block or via the P2P? Which is the optimal way for them?
Yeah, so attestations need to be broadcast via P2P because I am not likely to be the proposer of the next block, so I need to broadcast to all my peers on the network my attestation. They circulate around the network. They will later be packed into a block, but that's a much slower process. So yeah, it needs to be broadcast.
Okay, so if validator is selected as proposer for that particular slot, then they can send in the blocks also. Am I right or wrong?
Yeah, I mean, you'd include your own attestation for sure. Yeah.
Okay.
Yeah.
Thank you, Ben. Yeah.
All right, let me press on. How are we doing on time? All right, okay, need to get a move on. Right, let's talk about LMD Ghost. So this is the main fork choice rule that we have on Ethereum proof of stake. So the naming is insightful. LMD stands for the MD stands for message driven. So it relies only on attestations, and validators attest, this is what we just said, validators attest to what they believe to be the best head in the current slot. So if they've seen a block in the current slot, that's it. If they haven't at that 4-second mark, then they attest to the previous block from the previous slot. So it's message driven, that's the MD, and it's L latest. So only the most recent attestation from each validator counts. So there have been other variants, immediate message driven, fresh message driven, recent latest message driven. I'm not going to go into those. They're mostly passed into history. So just to say there are other ways that this could be done, but we use latest message driven. So whatever the most recent message from validator 10,000 is, that's its vote in LMD Ghost, which is its beacon block route. The ghost is more interesting. So this stands for Greedy Heaviest Observed Subtree Algorithm, Ghost, and actually dates back to a Bitcoin paper by Sompolinsky and Zohar. And it was really about what would happen if they decrease the block time in Bitcoin. It's 10 minutes, right, targeted, and made Bitcoin a bit more forkful than it currently is. Would it be Bitcoin uses the heaviest chain rule? Could they improve on that? And the answer is yes. Ethereum considered implementing proof of work version of this, but never did so. But we now have it under proof of stake, and we're going to look into it in detail. So that's the naming, and this is a sort of the key points about LMD Ghost. So its timescale is short. It's this 12-second slot-based protocol. So we're making a decision every 12 seconds about what the head of the chain is. And so it's relatively rapid for a global network. That's why we have to broadcast attestations via the P2P as swiftly as we can. And the goal is it's used for two things. So I want to find out what the head of the chain is for two reasons. One is if I'm proposing the next block, I want to know which block to build on that's least likely to be reorged out so that my block survives and makes it into the canonical chain. And it's used if I'm going to make an attestation in a slot. I need to know which is the best block to be attesting to in that slot. And the goal is that all of the nodes that share enough information will come to the same decision about this, and the network will converge on a single canonical chain. So that's the heuristic that we've spoken about. Which branch in the block tree is least likely to be orphaned in future? That's the one to be building on. And what we do is we weigh the votes that we receive in attestations. And I call it weighing because they're weighted with the stake that each validator manages, the effective balance of each validator. And it's important to note that in any given slot, so I've told you this is slot-based, it's happening every 12 seconds. In any given slot, only a maximum of 3 1/8% of the votes are fresh, so 1/32 of the slot. So every slot only 1 out of 32 validators is making an attestation because there are 32 slots in an epoch. So our new information in every slot is quite limited. We're only seeing the worldview of just over 3% of validators in each slot. And it's quite feasible that the other 97% of validators have a different view of the world, and we could be led astray by that. So worth bearing in mind. What are the properties of LMD Ghost? Well, it's live. It will always output a viable head block on which we can build. And there's a proof that exists of this under synchrony assumptions. Under asynchrony, there's a proof in the Gasper paper of it that it's probabilistically live. But needn't worry about these. These are details. It's basically live. It guarantees that you can always continue building the chain. As for safety, it doesn't give any useful guarantee. So LMD Ghost doesn't guarantee you any kind of any particular kind of safety. However, there is some ongoing work on a confirmation rule, which if you assume that you have less than 1/3 of the validators are adversarial, which we assume anyway, basically, otherwise many things would break, and you assume that the network is synchronous in some sort, or eventually synchronous, then you can say that after you've collected enough votes for a block, it will not be reorged out of the chain. So within a couple of slots, you can say that this, under these assumptions, that there is a block that won't be reorged out. So that becomes some sort of safety guarantee, but we're not currently using that. That's sort of for implementing it in future. There's a link there if you want to find out more about that. But assume for the purpose of this presentation that there are no safety guarantees in LMD Ghost. So what are we doing? Here is a block tree. We've got blocks A, B, C, D, E, F, G. Why has C not built on B? Well, maybe C didn't hear about B in time, so it built on the best head it knew of, which is A. Maybe it thought that B's block was invalid for some time. It received it in time, but thought it was invalid for some reason. Maybe C saw some juicy MEV in B's block and decided it wanted to steal it, and so reorg it out of the chain and steal its MEV. For whatever reason, C didn't build on B; it built on A. And likewise, for various reasons, other blocks have forked off. I've labeled each block with a number, and this is a sort of a number of votes, stake-weighted number of votes. It's sort of completely arbitrary in this example. So that's the latest votes for block F are 20, for block G are 10, for block E 25, and so on. And in pure LMD Ghost, A on the left, the root here would be the genesis block of the chain. So we go all the way back to genesis block in this algorithm. Now, this is the same diagram, but updated. And what I've done is on each line, I have put the weight of the branch. So each block has a weight. And if you sum the weights, so D and G add up to 20. So the branch leading to D has a weight of 20. B, D, and G add up to 40. So the branch leading to B has a weight of 40. And we can see down the bottom, F is 20, E is 25. If we the branch going from A to C is worth 60 because C, E, and F add up to 60. So that's critical for how the algorithm works, because we're looking for we're greedily looking for the heaviest observed subtree. So this 60 between A and C is the weight of the whole subtree descended from it. So the heaviest observed subtree is what we're after. And here's how the algorithm works. It starts at the root, which is A, and it follows, it finds the weight of the branches coming from A. There are two branches, and it follows the one that has the maximum weight, the heaviest branch, the heaviest subtree. So in this case, we go from A, not to B, but to C. And when we're at C, we just do the same thing again. We look at the weight of the subtrees coming off C, and we see that the one that goes to E is heavier, 25 rather than 20. And so we end up at E. And so we say this is our head block according to this algorithm. It's a different head block than if we applied a longest chain rule. That would give us block G. So we're applying the ghost rule. So we end up at block E. And that's it, really. That's basically how LMD Ghost works. Very simple. Here's some code which instantiates that. So we start with, it's called head, but it's a root at this point. We start with a root of the tree, which in the code is justified checkpoint root. But if, as I said, in pure LMD Ghost, that would be the genesis block. We'll come to this justified checkpoint thing later. And then we have this annoys me for reasons which I can't quite pin down, but this is a recursive function, but it's been written iteratively, which offends me. But anyway, what we are doing is iterating over the branches that come out of this block. So we start with the root, we find the children of the root block, and we get the weight of each subtree using this get weight function. And my greatest contribution ever to the Ethereum consensus specs is naming this function. So thank you very much. And we choose the maximum amongst the weight of these. So we get the weight of each of the children branches, each of the observed subtrees, and we find the maximum, and that becomes our new head, and then we go around the loop again. Now, nobody would ever implement it like this. This is horrifically inefficient because you're just repeating so many calculations. So either you need to do some quite aggressive caching, memoization, or you need a different algorithm. Proto Lambda has done a bunch of implementations of this a few years ago. One of them became Proto Array, which became popular amongst client implementations. Prism used it for a while. They moved away from it. I think Teku is still using it. But if you really want to dive into how this is implemented in practice, then you can follow the link there to that. But yeah, that's oh yeah, and then we are as for the get weight function, how do we weigh these subtrees? Well, we look for all validators that were eligible to vote for it, and we add up all validators that are eligible to vote at this particular time, and we add up their effective balance. So votes are weighted by the effective balance of the validator, as long as they are unslashed and active, but only if the vote is for a block that descends from the root of the chain. So when we're at the genesis, then the weight is every block in the tree, and as we go along the branches, then it's just the weight of the sub tree. So it's the weight of all the blocks that haven't for which the root block is the ancestor. The particular block is the ancestor. Is this, and then we return that. Ignore proposer boost for a moment. We'll get to that. So better in a diagram, we just add up all the blocks in the subtree here, and that's the weight. And that's LMD Ghost. Very simple. There are a couple of wrinkles to it here. We want to ignore undesirable blocks. So there are certain blocks we don't want in the block tree. We want to make sure the block is valid, that it was correctly signed by the expected proposer. This is actually checked upstream of fork choice, I think in the gossip layer, if I remember correctly. We want to make sure that all of the ancestor blocks of the block that we're looking at are valid. We can't, if there's an invalid block, then all of its children are invalid as well. We can't recover from that. So we exclude those. We want to make sure that the block post-state hash is correct, that did it respect the state transition function. That's the execution layer, state transition, and it's a consensus layer, state transition. So we have to rerun that and check it's correct. So those are basic validity checks. New in Deneb this time last year, we added blobs, and we have another check. We only include in the fork choice blocks whose data is available. If we cannot get the attached blobs for a block, then we ignore it until we can. So we can't make the head of a chain a block for which we don't have the data, or we can't get the data. In future, potentially, we might want to make sure that the block is non-censoring. So there's this fossil work going on, and that would exclude from fork choice any block that for which there was evidence that it was censoring, that it hadn't included the transactions which it was supposed to have included. Or if Ethereum becomes a government chain, maybe they want to only include blocks that do censor, for example, censor a tornado cache or something, but let's not go there. And in future, we might want to look at more sophisticated data availability, for example, peered as, rather than just checking the attached blobs. There are more sophisticated checks that we can do. And there's already some work being done on that for Fulu upgrade. And this is handled in the on-block handler. We needn't go into all the detail, but we check whether all its ancestors are there, check it's not from the future, check it's not too old. This is an optimization. Check the data is available. The next bit of code checks that the state transition function is correct, and so on. But this is where we filter out the undesirable blocks before they even get into the store, so we don't have to filter them later. Blocks for which data is not available may be held back and then become valid later, may be resubmitted. So that's this comment here. It may be queued and subsequently considered. in which case on block would have to be called again. Right, nearly there on LMD Ghost. Just want to talk about two more things: proposer boost and late blocks. So in 2020, a balancing attack was identified, and under some rather extreme circumstances, a very small number of validators could fork the chain into two equally weighted branches and balance the votes for them and maintain this split indefinitely. Proposer boost is the fix for that. So blocks, the way it works basically is that blocks that are received in a timely way by a node within 4 seconds of the start of the slot get a huge extra weight in the get weight calculation. And this extra weight also almost certainly makes the timely block the head of the chain. So that's the one that I'll build on. I'll declare the head. So this makes honest proposers almost sure to build on the timely block that they received. And this kind of principle is that a block that is timely should not expect to be reorged. You know, if I'm proposing a block in good faith, I should not expect my block to be reorged. I've got a link at the bottom to much deeper discussion of this. But how does it change our diagram? This is the same block tree that we had before. And how it changes things is that block G, which is the most recent block, you know, time goes from left to right here. If I received it in a timely way, then when I run the fork choice, it gets another 40 votes, 40% of the total testing weight in the slot added to it, which in this case would make, when we run our LMD Ghost fork choice, it would make G the head of the chain rather than E, which was previously based on attestation weight only. So if we include proposer boost weight, because G was timely, it gets an extra 40 points, and that makes it the head of the chain, and that's the one I'm going to build on next. Why 40 is a great question. It's had values, started off life at 25, then it went to 70, then it went to 33, and now it's 40. You can look it all up in the book. And this is how it works in code. I'm going to skip this because time is pressing on, but it's handled in get to weight and in get proposer score. This is where proposer boost is handled. Then you get this extra 40 points if the block was timely. And yeah, on tick resets that. So when I move from the current slot to the next slot, then proposer boost is reset, and so it no longer applies. So just for the duration of one slot, if I receive the block for that slot, it gets boosted and is much more likely to be the head of the chain. And so this the point of this was to mitigate the balancing attack, basically cure that balancing attack, and it's effective at doing that. But it also turns out it has another good use case. We can use proposer boost to fork out late blocks. There was a time when it looked like, well, in fact, nodes were demonstrably publishing blocks later and later. The publish time for blocks was creeping even beyond the 4 second mark, you know, 5.5 seconds into a slot. They weren't getting many attestations, but because they were received by the next proposer in time, they were often built on as the head of the block, ahead of the chain. Why would people publish blocks late? Well, it's all about MEV, and it's just having the maximum time to gather that sweet order flow and pack it into a block. Now, late blocks destabilize the network. They don't gain many attestations, and this leads to confusion and forking and reduces the reward for honest validators who attest to an empty slot that turns out later not to be empty because the block was late. So we want to discourage late block publishing. Proposer boost allows an honest proposer to build on the parent of a late block, and the honest proposer's block becomes the head. So as long as I propose my block in a timely way, then I can build on the head of the previous, I can build on the parent of the previous block, and my block won't get orphaned. And that's and there are lots of caveats there, and I won't go into it in detail. But the idea is we can use this extra power that a timely proposer has in order to fork out late blocks and punish them. And it's been great. It's pretty much cured the problem. So hallelujah. Last topic, I think, on LMD Ghost, slashing. So early proof of stake designs had a real problem because nothing was at stake. I mean, stake was used as an anti-Sybil mechanism, but wasn't used for anything else on there. So it was basically just to limit the number of participants on the network because if there's, however, nothing was really at stake. There were no sort of punishments there. And that meant that equivocation, which is changing your mind or supporting two forks simultaneously, was costless. It's costless for proposers to publish multiple blocks. So why not build on every head? I mean, why do I need to choose one? I can just build on them all, and I'm guaranteed to be in the canonical chain. And also it's costless for validators to vote for everything they see, which is a rich source of attacks. So the solution to this is slashing. Vitalik proposed this in, unbelievably, January 2014 with Slasher. We don't really use any of the Slasher mechanisms now, but the idea that you can punish stakers for bad behavior solves the nothing at stake problem and actually made proof of stake a viable consensus mechanism. Well, it's not a consensus mechanism, but a viable approach to fork choice. So yay, we have a consensus mechanism. This is the summary I showed you before. LMD Ghost, perfectly good consensus mechanism. And, you know, if we were just using that, Ethereum would probably run fine. And we could just crank out blocks via LMD Ghost and be happy with the world. But the idea is we can do better because we have two features under proof of stake. We have a well-defined set of participants. We know who the stakers are effectively. You know, they have an on-chain identity. It's a closed set, unlike in proof of work where anybody can be mining on the chain. And we can do slashing. We can apply economic penalties for bad behavior. So how about we use these properties to add some stronger safety properties to our chain? And that's where we get to Gasper FFG. But I am going to pause for breath and take questions. Questions on LMD Ghost?
Yeah, so you mentioned that LMD Ghost doesn't give us finality, which is about what I think what you're going to talk about now. But you also mentioned that there's this confirmation rule that maybe people were working on where you could get things stronger from LMD Ghost. And it really sparked this memory of like Vlad Zamfir and CBC Gasper. And I wondered, like, if that's too off topic, no problem. But I wondered, like, are those similar, or is this confirmation rule that you talked about like different in some way?
Yeah, I don't think it owes anything to Vlad's work. And you can take a look. You may be more familiar with CBC Gasper than I am, but you can take a look at the link that I put there and see how it is constructed. From my rudimentary knowledge of CBC, it is not similar to that. But you know, there's a lot of information around on the network to guide us, and so if we make some simple assumptions, we ought to be able to do better than waiting 12 minutes for finality. Yeah, that's the idea.
Okay, thanks.
Hi, Ben. Thank you for the talk and especially for the book. Could you please briefly explain justification, why the protocol needs it?
Yeah, we're going to do that. That's next.
Oh, okay. Thanks.
Yeah. So in get head function, we are using the justified checkpoint to fetch the head of the chain. So is it because LMD Ghost doesn't ensure the finality and justification is happening on every block, every epoch, not and finality is happening on every two epoch?
We'll come to that in the Gasper bit when we get there. Remind me if I don't answer that question there.
Perfect. Yeah. Thank you.
Right, let's press on. Still, time is going more quickly than I expected, as usual. We'll look at Casper FFG. Okay, so LMD Ghost is a perfectly good consensus protocol, but we've decided we can do better. So we have this Casper FFG thing, and the naming again is instructive. I mean, the Casper is a bit obscure and random, to be honest. I mean, it's just got in there for historical reasons I won't go into. FFG is a friendly finality gadget. So the friendly is Casper the friendly ghost, but it's a friendly finality gadget. A gadget is what Vitalik calls a kind of self-contained enhancement to another process. So Casper FFG is a gadget for adding finality to an existing blockchain consensus mechanism. So it was originally actually planned for adding finality to proof of work as part of the proof of stake transition. That's EIP 1011, which Danny Ryan was heavily involved in. And it was, so proof of work doesn't have finality. And the idea was that Casper FFG could be overlaid on top of it with bringing some elements of proof of stake to bring finality to the proof of work mechanism. However, we have adopted it instead for to overlay it on LMD Ghost. And oh yeah, the original paper is really nice, actually. It's worth a read. I do recommend it. So what are we doing with this? Timescales of Casper FFG. It operates on the timescale of minutes, epochs. So an epoch is 32 slots. And 6.4 minutes. So the timescale is, 6 or 13 minutes. The goal is to confer finality on the chain. So this means that the chain will have a checkpoint, and I'll tell you what a checkpoint is later, a checkpoint that will never be reverted. So it will always exist in the canonical chain and all of its ancestors, of course, except at enormous cost. So we can revert a checkpoint, but if we do so, then we have an enormous quantifiable cost, which some attacker will have had to pay in order to do that. And it uses a two-phase commit. Alex talked about this, I think, in his presentation, which is a classical sort of consensus mechanism approach. So among validators having at least 2/3 of the stake. So we need 2/3 of the stake to be honest. As long as that's the case, we can achieve finality. And we'll talk about that a little more. And we weigh source and target votes received in attestations, but we only consider attestations that are contained in blocks for this, because it makes changes on chain. Finality is updated on chain. We can only consider attestations that are in blocks, because attestations on the wire on P2P are ephemeral. They can be lost forever. Blocks are forever, though. And it has properties which are analogous to liveness and safety, because it's an overlay. It's not. It doesn't have its own liveness in a way. It's not producing blocks, but it has a sort of plausible liveness, which means that Casper FFG can never get into a stuck state that is unable to finalize anything. So in other words, Casper FFG can always have a go at finalizing another checkpoint without having to slash participants or unnecessarily. And it has an accountable safety property. So if less than 1/3 of your stake is honest, then it's fully safe. It offers you classical consistency. But if more than one, you can never know if less than or more than 1/3 of your stake is adversarial or not. But even in the case of more than 1/3 being adversarial, then it has this accountable safety. Finalizing conflicting checkpoints comes at enormous cost. So we call this economic finality. So those are the properties of Casper FFG, and we add them, layer them on top of LMD Ghost. Casper FFG works on checkpoints. So it relies on being able to see votes from the whole validator set. And that's too expensive. You can't have every validator attesting at every slot. That would be, currently 1 million attestations every slot going around the network. It would just overwhelm things. We only have 3% going around the network every slot for that reason. So what we do is we actually accumulate votes across an epoch. So we have 32 slots, and we do 3% or 3 1/8% each slot. And then by the end of the epoch, we've got all the votes for that epoch because every validator has voted once. And then we do the accounting for Gasper FFG at the epoch transition. So this is this solid line on the right, and at the beginning, the epoch transition to the next epoch. We add up all the votes and we figure out have we got justified and finalized checkpoints. So a checkpoint is the block in the first slot of an epoch. So we can see at the bottom the checkpoint object. It contains an epoch number and it contains the root of a block. So it refers to a block in the first slot of an epoch. If there's no block there, then it will be the block that's most recent on that branch is the checkpoint. So every epoch has one checkpoint unless it's branching, unless it's forking, in which case it might have multiple different checkpoints, but it's always the first slot of the epoch. And validators vote. So we're going back to our attestation data. We've looked at the LMD ghost vote, and at the same time, validators make an FFG vote, and they vote for a source and they vote for a target. And these are checkpoints, that data structure that we have here. They vote for an epoch and a block root. So the source is the highest justified checkpoint I know of. So in my store, I've got the best justified checkpoint I know, the most recent one. And so when I make an attestation, that's my source vote is for that checkpoint there. This is justified. And the target is whatever. So assuming we're in epoch n+1, the target checkpoint is the checkpoint of the current epoch. So I vote from source to target, and we can imagine it as an arrow, sort of curved arrow here is my vote. And if I see more than 2/3 of validators by stake weight making the same source target vote, then I have what's called a supermajority link. So a vote is a link between source and target, and a supermajority link is when more than 2/3 of validators have made the same vote for that. So this gives us this sort of two-phase commit, and this is a bit tricky, and I go into it in much more detail in the book, and we haven't got time really to go into a lot of detail, but basically what we're saying is justification. So my target vote says my preferred branch has current checkpoint X, whatever the checkpoint of my current epoch is. Then if I hear that 2/3 of the validators agree with me, so I get votes, I receive attestations with target for the same checkpoint from 2/3 of validators, I can then mark X, that checkpoint, as justified. So I'm saying when I make an attestation, I'm saying I like X as the target vote, and I'm receiving from other validators their attestation, their target vote, and they're saying they like X as well. So as long as I get more than 2/3 of them agree with me, then I justify that checkpoint X. My source vote is saying I heard that, so it's reflecting back to the network what the network has just told me, and this is why we have two phases, and it's classic part of the mechanism and very hard to explain, but you can read more about that. My source vote is saying I heard that more than 2/3 of you like X, so I justified it, and you broadcast that to the network. This is my justified checkpoint. If I hear that 2/3 of validators also said that they justified checkpoint X, I can mark it as finalized now. The point is that when I justify a checkpoint, that is my commitment never to revert it. I effectively is locally finalized for me. Now it's not finalized globally because I don't have a global view, but it's finalized locally for me because I've heard that 2/3 of validators out there like that, and so I commit to never reverting that justified checkpoint. Now, they might be lying to me, which is why I need to do the second round and finalize it. If I hear from 2/3 of validators that they have also justified it, then we have this kind of global property that checkpoint then becomes finalized in the protocol. And it's a little more subtle, and I'll show that in a moment. But effectively, justification is my local version of finalization. I will never revert justification as a node because basically I'll get slashed for it. So you can think of it as finalization is just a kind of cherry on top. It's not a big deal as a node. The key thing is justification, and that might answer, I think it was Raj's question earlier. Now, there are Casper commandments. I'm not allowed to make a double vote, so I can't vote for the same target in two different attestations. So if there's a linear chain, I can't vote twice for the same target in epoch 3 here. That's not allowed. And if there's a fork in the chain, I can't vote, for the same target there. So same target from two different justified checkpoints on the linear chain, or different targets at the same height on a forked chain, with the same source vote there. Those are no. And the other commandment is no surround vote. So that's what it is, technically at the top, the technical statement. But surround vote's easy to see. If my source and target vote surrounds another vote that I have made, or is surrounded by another vote that I've made, then I also that's also against the commandments. That's also forbidden. So on a linear chain, it looks like the diagram on the left. The diagram on the right is interesting because this is actually what happened on Holsky after the upgrade. Briefly, the bottom fork was the majority fork, which was faulty. They had the wrong deposit contract address or unconfigured deposit contract address, but enough of them forked off with that they were able to justify a checkpoint on the faulty chain. However, they are not allowed to rewind justification because that would result in them making a surround vote because the chain has moved on. So all of the validators, if they want to try to rejoin the correct fork, which is the minority top fork, they will get slashed, and we'll come to slashing in a minute. They will have broken this commandment, shall we say, for now, no surround vote. So there's a nice, juicy real-life example of this rule in action. And I've spoken of the properties of Casper FFG. There are proofs of accountable safety. There are proofs of plausible liveness. They're very nice proofs, actually, quite simple. And I've linked to them here in my writings, though you can also see them in the original Casper paper. And there is one further rule that is required. We only finalize a checkpoint that is direct child of a justified checkpoint. So in the top diagram, epoch n checkpoint is justified epoch n plus 2 because we have a supermajority link from n to n plus 2, but epoch n plus 2 checkpoint we don't finalize in this circumstance. And if you work through the proof of accountable safety, you'll be able to see why. It just becomes glaringly obvious. So we only finalize a checkpoint when its direct descendant, the checkpoint in the next epoch, is justified. And finalization, but justification is the most important property. Finalization is just a kind of nice cherry on top. And of course, everything in Ethereum is more complicated than you hope it is. So actually, we're doing something more sophisticated than this called K-finality, but you can read about it there. But this is the original Casper vision. Slashing. What we do is that if either of the commandments are broken by one or more validators, we slash them. And this guarantees that if more than 1/3 of validators are faulty or adversarial, so they finalize a conflicting checkpoint, then at least 1/3 of them must have broken a commandment, and we can detect it and we can prove it on chain. The code is very simple. You can check it there. And the aggregate cost to an attacker, if it's one attacker doing this, would be at least 1/3 of the total staked ether, which is what 10 million ETH or something at the moment, which is vast, even at today's prices. So we have this economic finality property, a quantifiable cost to messing with finality, even if the attack has more than 1/3 of the validators. And this is an amazing breakthrough. If under classical consensus mechanisms, more than 1/3 of the replicas validators are adversarial, all bets are off. I mean, generally they halt or go haywire. So being able to put a cost to attacking the chain is very powerful. Okay, quick pause there. That's Gasper FFG. We're going to look in the final section. It's only a few slides at how they're combined into Gasper, but I will, as promised, just pause there for questions about Gasper FFG, and I'm aware that I have gone through it swiftly, so apologies for that. Yeah, let me press on. Just a few more slides. Okay, so we've got these two. We've got this gadget and we've got this consensus mechanism, LMD Ghost, fork choice rule. We've got this finality gadget. How do we put them together? This is Gasper, inelegantly named. And basically, it looks like this. We have our usual blockchain, block tree going from left to right. The first part of it is finalized by Gasper FFG. We have a finalized checkpoint. Everything before that checkpoint is guaranteed to be linear. We have one canonical chain and a very nice clean history. Any branches off that chain have been pruned out and are lost in the mists of time. But in the more recent past, after the most recent finalized checkpoint, and there's an argument to say justified here. I won't go into that, but think finalized for now. This is the domain of LMD Ghost, and it operates for the last couple of epochs since we last had a finalized checkpoint. So everything up to about 2 epochs ago is nice and clean, and then from 2 epochs ago we have LMD Ghost operating. And how do we combine them together practically? Well, we apply Gasper FFG's fork choice criterion. We follow the chain containing the justified checkpoint of the greatest height. So the highest justified check. So pure LMD Ghost starts at the Genesis block. A would be Genesis. But if we apply the Gasper FFG fork choice, then the root of our LMD consideration is the highest justified checkpoint that we know about. The highest finalized would be earlier than this, but we've already committed as a node never to reverting block A because it's justified, so we can start there. There won't be any other branches that are interesting that we need to explore. So that's it. That's basically it. When we run LMD Ghost, we just start from the highest justified checkpoint, and that explains where this comes from. We looked at get head function previously, and this is the route where we start our search when we run the get head algorithm. We apply the Gasper FFG fork choice rule, and there it is. The world, if that were the end of the story, which it isn't, unfortunately, this is what it looks like in reality. How LMD Ghost and Gasper FFG are actually bolted together is ugly. Vitalik agrees, and you can look at the quote from him later. I skipped over this. Get head has this mysterious function, get filtered block tree. Where does that come from? That's not in the Gasper FFG paper anywhere. What it's doing is removing from fork choice consideration, by removing from LMD Ghost consideration, any branches that had non-viable heads. What is a non-viable head? So this is So here we are. If we start with the justify block, this is the second block from the left here. We've got our block tree, which we're feeding to LMD Ghost. But before we run the get ahead algorithm, we're filtering out some branches with non-viable tips and removing them from consideration. A block is non-viable if the state that's associated with that block does not agree with my store about the current justified and finalized checkpoints. So the block is associated with state. It was built on a particular state, and it contains the data that transitions to the post state when you run the block, and that assumes a certain justified and finalized checkpoint. But it may be that that state associated with that block doesn't agree with the state that I have, the view that I have of the world. And so we have to filter it out of the LMD Ghost fork choice. And this resolves a finalization deadlock issue that was found, which is a failure in plausible liveness, one of the properties of Casper FFG. And basically, LMD Ghost and FFG have a sort of conflict. They're hard to kind of wrestle into conformance with each other there. So we filter out branches with unviable tips from consideration by LMD Ghost, and so that was all very nice for a while. And then we discovered another problem, which is unrealized justification and finalization. So where this stems from is that what we do, the way we accumulate Casper FFG votes is gradual. We accumulate them slot by slot. And it could be that by 2/3 of the way through an epoch, we already have enough votes to justify this checkpoint N. So, but we won't actually mark it justified in the state until we get to the end of the epoch when we run the state transition, the epoch transition. So we call this an unrealized justification. We've got enough votes to justify it, but we haven't actually justified it yet because that's only done at the end of the epoch. So that can happen, when you're 2/3 of the way through the epoch slot, but around slot 21. And this leads to an unrealized justification reorg attack, which means that the proposer of the first block of the next epoch can fork out up to 9 blocks from the end of the previous epoch. Details are in the link. Then another attack was found whereby an adversary can reorg arbitrary numbers of blocks from the start of an epoch. And the issue with this is that the filter block tree function was being too aggressive in filtering out potential heads of the chain because it didn't account for this unrealized justification. So blocks that would match my checkpoints if they had gone through epoch processing but hadn't, so it was unrealized, were marked as non-viable, whilst actually near an epoch boundary they were viable, and so on, and they were removed from fork choice. And this leads to reorgs and so on. So this is really by way of saying you need to follow the links to really kind of dive into this, and it's very hard to reason about. But really by way of saying that this nice, neat combination of Casper FFG and LMD Ghost is actually a mess. The answer is single slot finality, yay. And that's the end of the presentation. That's you've got about 10 minutes if you want to ask me questions.
Hi, am I audible?
Yeah, we hear you.
All right, nice. So I'd like to understand, because so far the upgrades have been very, similar. It sort of bots in together, one layer on top of another. But in this single stop finality, I'd like to understand, practically, how do the protocol actually does a consensus fork, because the execution fork is quite simple. You just drop off the transaction ultimately, but I think the consensus fork is something that's very hard to implement practically.
Yep. Yeah, it's a good question, and I don't think we've really thought through the mechanics of it yet. I suspect that it will get punted to Justin Drake's effort on what used to be called the beam chain, which is changing name now. So just as we built the beacon chain alongside proof of work, and then we shifted the execution layer over to the beacon chain, Justin and teams are working on what used to be called the beam chain. I don't know if it has a new name yet, which is really the next upgrade in the consensus layer, next massive upgrade, and uses a lot of ZK proofs and so on, with a maybe 5-year time horizon. Potentially that could deliver single slot finality. And we'd do the same. We'd do another merge. We would take the execution layer off the beacon chain and then put it onto the beam chain, and run it from there. So rather than upgrading the live consensus mechanism, we would kind of lift and shift the execution layer again. We've done it once, we can do it again.
I see. Thank you.
Well, I'm amazed. You got a lot of stamina, people. Feel free to ask me about any non-consensus stuff if you want a bit of light relief as well. Happy to talk about TechQ or other things. Yeah, I'll catch you.
Yeah, I wonder if Gasper has been changed through the hard forks or not, or it's stable and solid.
Yeah, it's a good question. So there are some aspects that we so fork choice, you don't have to upgrade through a hard fork generally because it doesn't affect the state transition. So you can more or less roll out changes whenever you like. So when we implemented Proposer Boost, for example, clients rolled it out kind of when they were ready, and just generally, within a few weeks of each other. It didn't break the chain until it did. And I've got a section on this in the book. It did actually lead to a very long reorg because some clients were using Proposer Boost and some weren't, which doesn't technically break the chain. It's not a hard fork, but it caused a certain amount of chaos because long reorgs are not desirable. So in principle, we can do uncoordinated upgrades for most of this fork choice stuff, but in practice, we try to coordinate them not as hard forks, but as very tightly coordinated upgrades between the clients, just so we don't risk having another long reorg. Does that answer your question?
Yeah, so it means that phase 0 is the basic spec, right, for fork choice.
Yeah, and phase 0 fork choice spec kind of keeps getting updated all the time. So it even though it says phase 0, it's not the fork choice that we started with. It's more or less the current fork choice, and changes to fork choice like the filtering function and so on get kind of backported into the phase 0 spec. I'm not sure what the rationale is for that. Presumably because they're not associated with hard forks. They've been done outside of hard forks, maybe.
Thank you.
Yeah, so in one slide, I saw that the nth epoch was justified and the n plus 2 epoch was justified. So what happens to the n plus 1 epoch? Like, can it be justified later?
What happens to an unjustified epoch? When an epoch becomes finalized, when a checkpoint becomes finalized, then implicitly everything prior to it becomes finalized as well. So it's a bit of a technicality, really. I mean, in principle, when an epoch becomes justified everything before it is effectively justified. We just don't call it that, because we have to track whether the direct descendant of a justified epoch is justified in order to declare it finalized. So really what you're looking at is the finalization, and that just effectively finalizes everything before that finalized epoch. But yeah, it's not really useful to think about the state of epochs before the last justified one. They are what they are.
No, I don't like. I didn't get it. Like, what happens to that n plus an unjustified epoch?
Yeah, I mean, it just doesn't matter. It just sits there. I mean, the chain moves on, and we try to justify new epochs, and eventually we'll finalize something, and everything prior is marked as finalized. Because we're always dealing with the highest justified. Our source vote always comes from the highest justified epoch that we know about. So we don't care if the previous epoch was justified or not justified. It's just irrelevant to us. So we're only ever interested in the highest justified epoch that we know about.
Okay.
Hi. I would like to ask, base roll ups versus sequencer base roll ups, which would you prefer and why?
Oh man, that's a good question. Yeah, I'm too fresh from my optimism experience to be objective about this. I need to I need to spend more time looking into the whole base rollups and native rollups and all of that scenario. So I'm going to dodge that question. Yeah, sorry.
Thank you.
Yeah, like I saw that there are many implementations of the consensus client, but what they differ mainly is the language that they're implemented. So, is there any other difference in them, or it's just that?
Yeah, I mean, it's quite interesting I was like product owner for Teku for years, right? And it's quite interesting being product owner of a product which effectively has to be identical to all the other products. The behaviors cannot differ in any meaningful way from between Prism, Teku, Lighthouse, Lodestar, whatever, because otherwise it would be a fork. So it's kind of a bit of a weird role. They tend to differentiate on things like amount of disk space used. Teku, we worked really hard on the RPC interfaces so that it could be used by Infura and others, so that they were super responsive. So they tend to differentiate on features, but the base product, the state transition function, and all of that, the gossip and all of those things, basically identical between the clients. So yeah, reliability, uptime, and so on. You're always looking for that little performance edge, but fundamentally, there's not that much to choose between them these days.
So, won't the
Mm.
Hello. Hi. Yeah, I just wanted to ask about there is this two round of voting in the slide number 40. Like you said, the proposer gets like I like X. Then he says I heard you like X, and
Mm.
then they all revert it, and then it's finalized. So this makes it two-stage process. So like there is some material or like you could discuss about it like.
Yep. So this is a two-phase commit. So you can look at the original PBFT paper if you want the sort of more academic view. I've written about this at length in the book. You can look at it. only matters in the most adversarial environments. It's really, really hard to come up with an example where justification is not the same as finalization. And I've got one in the book, but it's very contrived. Is in reality, justification and finalization are almost always going to be equivalent unless you're in an extremely hostile network. But in order to prove things, in order to guarantee finality, you do need to do this 2 phases. You need to hear from everybody and broadcast that, and then you need to hear from everybody that they heard what you said and double check everything. You can look up the Byzantine generals problem. That covers this, which is the original work by Leslie Lamport. And if you really want to test your reasoning about this stuff, I put a cheeky link in the EPS GitHub announcement of this call to the blue eyes problem right at the bottom of that page. If you spend a couple of hours thinking really, really hard about that problem, if you manage to solve it, then you pretty well understand consensus mechanisms, I would say. You will get deep insight into this 2-phase commit thing. So recommend that if you want to kind of get deep knowledge on what's going on here.
Yeah, that's great. Thank you.
Yeah, thanks all. Good luck with the rest of your studies, and look forward to seeing you on Core Dev calls in years to come. It's been a pleasure. Thanks, Mario.
Thanks, Ben. Bye.
Record